Hopefully you should see them now.
Yes.
Yes, okay. Hi, my name is Joe Rowe. I work with the Center for the Study of Early Agricultural Societies at the University of Copenhagen. I'm not a zoo archaeologist or an archaeobotanist or a geoarchaeologist. I'm coming more from the perspective of an enthusiastic consumer of open data in archaeology. And so I have a very selfish interest in the subject of this meeting. My work relies pretty much entirely on data that has been produced and made available by others. So I'm first very grateful to the organizers for making this the topic of our discussion today, and very excited to be hearing about all the progress being made on that front. Specifically, what I'm interested in and what I want to talk about today is how open data can be used to build models of past environments and past ecosystems on a regional scale, and particularly thinking about recently released data from climatology and ecology. So I'll be using a couple of case studies drawn from ongoing work on the agricultural transition in Southwest Asia, in particularly the arid parts of the southern Levant. But the basic question motivating this work is one which I'm sure many of us share, and it's just simply, what was the ecological world that the people we study lived in? Of course, site-based archaeology tells us a great deal about the past environments in particular times and places. But what I think can often be missing from that picture is that regional context. It helps, of course, to compile data from multiple sites, as we've seen several cases of today. But for the specific purposes of paleoecological modeling in archaeology, in my experience, it's quite difficult to do this bottom-up interpolation of records into a regional picture. So what I like to experiment with is more top-down models of paleoenvironment and paleoecology, using, for example, global climate, global environment, global terrain data. And the idea is that these will complement, contextualize, and ultimately can be compared to the signals we get from the archaeological record. So as an idea of what I mean, the kind of regional reconstructions we usually have, at least in Southwest Asia, are what you might call these expert knowledge models, where the available empirical data is sort of integrated into an interpretive map. And these are often the foundation for computational models of human ecology, human subsistence. For example, this study of foraging ranges in the southern Levant on the right. And so without at all downplaying the usefulness of these informal models, they do have a few limitations that make it hard to use them in formal paleoecological modeling. They're quite coarse, they're aggregated into these sharp zones when the reality was probably a bit more fuzzy. And probably most notably, the methodology behind them tends to be made neither explicit or transparent. And so when you have a situation with fairly major disagreements between different models, it can be quite hard to decide which one you should trust. And I would propose that it's overcoming these kind of limitations where computational modeling can contribute. So one potential approach to adding detail and transparency to these kind of regional reconstructions would be ecological niche modeling, which I'll take as my case study today. I will talk more about the method in a bit, but the basic idea is that these predict the distribution of a given species in a given environmental space, in this case, a paleo distribution. So the species I've modeled here is wild barley in the southern Levant, which was, of course, an important component of later agricultural economies, but also occasionally exploited by epipaleolithic foragers sites like the one indicated on the map in interesting ways. So the model was trained using data on contemporary occurrences of this species in relation to its present environment. And then this was projected backwards using paleoclimate reconstructions at key intervals over the past 20,000 years. For example, the Younger Dryas pictured here. So a simple takeaway would be that Bali is or was more readily available to the people at this site when it was occupied compared to today. And hopefully you will agree or see how this gets us a little bit closer to a more nuanced picture of the regional environment around this particular site. But I don't want to dwell on the results today. I want to talk about the data and the tools that produce them. So as I mentioned, this uses a method called ecological niche modeling. It's also called species distribution modeling, and very extensively used in ecology to model species ranges. And the two main inputs are, on the one hand, georeferenced occurrences of the species or set of species that you want to model, and then a set of environmental predictor variables that you assume is relevant to the distribution of that species. So these two broad categories of data are used to train a model. In my case, I used a regression model. There are other ways of doing it. A model of the niche of that species in relation to those environmental predictors, which you can then take and apply to another context, in this case, another time. ENM is not new in archaeology by any means. Here are just a couple of examples from Southwest Asia, so models of Neolithic cattle and also foraging, plant foraging around the site of Boncuklu in Turkey. And indeed, it has been pointed out that this is probably generally a very useful method for our discipline as a whole. I've also been sort of dabbling with it for quite some time now. And what's really struck me in recent years, and what is the motivation for this talk, is just how much easier it has become thanks to new open data and open methodological tools that we've now have access to. And because of these data sets, we can now take a slightly different approach to the approach that was generally used in the studies I've shown there. In those studies, it was usually present environmental data and past occurrences, whereas I've now switched it round. So using present occurrences and paleoclimate reconstructions to do the predictions down here, although present environmental data is still used for the training. And this largely follows the availability of data, which I will come on to, but also a recommendation by Franklin and colleagues in this paper here, that it is probably more robust to train the model on one set of occurrences and use another for verification. So a missing step here might be to test these predictions against occurrences from the archaeological record, which I will return to at the end of this talk. So this model relied pretty much entirely on open data sets, mostly ones that are only available in the last few years. And for the substance of this talk, I'd like to quickly run through what those are and why I think they have a potentially wider application in paleoecological modeling for archaeological purposes. So in terms of occurrences, those georeferenced records of where species are found, I used GBIF, as most people doing ecological niche modeling now do. This is a very comprehensive database of databases of the type we've talked about today, which aggregates multiple national and regional occurrence data sets into one metadatabase with a very nice, well-designed web interface, but also, crucially, a robust API for programmatic use. And this includes occurrences of both plants and animals, so can be used for modeling either. In terms of the environmental predictors, climate are usually the key variables, and the standard for many years in ecological niche modeling was WorldClim. The first version has been around for at least a decade, I think, and this was an interpolation of data from meteorological stations over the last few decades, with a couple of reconstructions of past climate slices, but not too many. And WorldClim, like most data sets of this type, uses a system of coded bioclimatic variables, which are basically a series of indices that are all ultimately derived from monthly precipitation and temperature data, and are thought to be particularly relevant to determining species niches. But since 2017, we have a few new options, coincidentally all released in the same year. So all these three data sets offer climate surfaces of the whole globe at a relatively high resolution, and they differ primarily in the methodology used to construct them. So WorldClim 2 is an updated version of the interpolation method of WorldClim 1. Meraclim uses remote sensing data, while Chelsea uses predictions from global circulation models. So these are the gargantuan simulations used by climate scientists to model current and future climate change. In terms of choosing between them, I don't really know. The results look pretty similar to me. I think from the modeler's point of view, what's great about them compared to previous data sets is that they provide a nice high resolution, they provide global coverage, and they include monthly time series data, as well as the aggregated bioclimatic variables, so that you can look at things like seasonal variability in more detail. And speaking of paleoclimate, so this is what I would say is the most exciting development in recent years in this area. That is the application of these kind of climatologies to past conditions. So Paleoclim is a fantastic data set of high resolution paleoclimatologies covering key parts of the Holocene and Pleistocene. And these are derived from a combination of global circulation models and the modern climatologies like Chelsea from the previous slide. Paleoclim in turn is based on PaleoView, which is a handy tool that allows you to use the same method for any arbitrary time slice or region. When you're modeling plants, especially, I think it's also useful to take into account the terrain. And here we can benefit from soil grids, which is, again, a nice high resolution global data set of soil characteristics derived from remote sensing, as well as the classic DEM digital elevation model, which I don't think I need to say too much about, other than to point out that we now finally have NASADEM, which is the improved 1 arcsecond resolution global DEM from NASA. So those are the data used in the ENM. We can point to many other recent data sets that might be useful. Just sort of thrown in some ones I've come across recently here. Would point to StableClim. Looks particularly interesting. It's like Paleoclim, but for climate stability indexes. And this is, yes, surely not a comprehensive summary, but a selection of data sets that I use regularly. And what I really can't emphasize enough is how much easier it's made the work compared to just, say, 5 years ago. They do also have a few key characteristics, which I think is what makes this possible. One is that they're open, as we're talking about today, always good. But another is that following the FAIR principle, they are machine accessible. So they either use well-known distribution formats or like GBIF, which is a living database. It has a nice, flexible and robust API for programmatic use. Just quickly, as an honorable mention, to use these nice open data sets. There are also some recently released open tools that make it much easier. So my modeling is based in R. One could also use Python, etc. And this allows us to take a script that is developed for one analysis, like the Hodium example, and very quickly extend it to a whole range of different contexts. So here, different species, different time slices, things like that. R is enhanced by many packages for accessing open data, many of which come under the umbrella of the R OpenSci project. So for example, I used RGBIF to access the GBIF data programmatically. And I could quickly plug my own package for accessing Paleoclimate data, which I hope to submit to R OpenSci soon. In addition, there is, of course, all the methods-specific packages. This model used SF, it used tidyverse, it used Dismo for ENM-specific methods, and it used raster for geostatistics. And we can now add to that a small but growing number of packages specifically for archaeological data. Running out of time, I think, so I will not go in detail over what I think could be some other applications of this collection of data and methods, or data and tools. I don't think it's limited to the ENM method. I think it is perhaps something we can use in many applications, and in terms of open data in archaeology, the success of open data in climatology and ecology is perhaps somewhere we can look for inspiration on how to solve some of the challenges that we've talked about today. Thank you very much for your attention.